research here. First of all, let's just briefly introduce myself. I got my bachelor and master degree in China, working on railway engineering since 2009. And after that, I started my PhD in Delft University of Technology in Netherlands. And during that, I visited Southwest Georgia University, which is the best university doing railway in China. And we had a lot of communication there, and I enjoyed the food there a lot. And then I started my postdoc also in Delft University of Technology, working on several EU-funded projects, and also Pearl is more like network rail. And for example, like shift rail into zone is about the transition zone, railway transition zone. And also make for rail is about the magnet-derived railway system. It's more about a maglev train and air levitation train. STEM is about the railway system vibration. And after that, luckily, I got a Marie Curie postdoc fellowship. And then I started my journey in University of Birmingham. I meet a lot of talented guys here, and good to see you all here. And here is the video I made. It can be a framework what I did, and what I would like to do is more like inspection, and also using AI and digital twin to analyze the problem, to give some advice or maintenance, repair and reuse, all this kind of stuff. I made this video because we also would like to cooperate with the pavement engineering, not just a railway engineering. So we use this vehicle that can run on the road, and also it can run on the railway track. And this is a framework of my research, and also what I'm working on. First step, we get the non-destructive testing inspection data from the state-of-the-art technologies. For example, the LiDAR, light detection and the ranging for the track geometry, and also the 3D camera for the track components, for example, like a rail, sweeper, fastener, and ballast. These technologies are for the surface, like point clouds or whatever. And we also need to analyze what is going on inside of the components, for example, like the ballast layer. So we use ground penetrating radar to see what the problem inside of this kind of ballast layer. And then we go to the step 2. Step 2 is we use machine learning to process these NDT inspection data, because there are huge amounts of data. Every time we go to the field, we get maybe at least 100 gigabyte data. It's already compressed, and yeah. So we do really need this machine learning to process the data. And then also, I will explain later, it's kind of very tedious job to just watch to see the data manually. And we go step 3, we use the AI enhanced NDT data to build the digital twin, because the digital twin is different from normal digital twin, because we use this coupled multi-body simulation, discrete element method, and finite element method. This is the very novel way of building the digital twin. And then with the digital twin model, we go step 4. We to do some track defect diagnosis and prognosis, and also this will get when to inspect the track and when to maintain the track. And then we go to inspect the track again. Then we get inspect data. Then the data constantly update the digital twin model, so it becomes a whole loop. Use this whole loop, we can finally go to the step 5. We would like to achieve railway circularity to meet the net zero or this kind of purpose. It is a decision-making system for repair, reuse, and recycle and repurpose all track components. For example, here is an example for the railway track component. The rail is the rail steel rail. And let's first see the motivation of using ground penetrating radar, as I explained earlier, is because we would like to know what is going on inside of the ballast layer and also the embankment, the subgrade, because usually it is not visible. For example, like the soil or the degradation or the falling, uh, it has started to accumulate at the bottom layer, and then it goes to upper layer and finally to the surface. So if we would like to know what is going on, we have to use ground penetrating radar at the early stage. Then we know what something is going to happen. And then what we do is we build a full-scale test track. First, this is the simulated slot is a really deep slot, and then we fill the subgrade with some soil and also with sand to simulate the field conditions. And then we build a clean ballast, forward ballast, and then finally we get the full-scale track model. Then we use the ground penetrating radar to do some tests to collect some data. And then next step is to analyze the data. Here is the one signal, how one signal looks like. It can clearly distinguish where the air, where the ballast layer, and if the ballast layer is dirty or clean, there are some different shapes of this signal. So we developed 4 indicators based on these characters, and then using these indicators, we can distinguish or tell which part is clean, which part is dirty, which part is fault. This is the basically the principle. And then we goes to the field to validate our approach, our method, our technology. Let's say technology, better word. And we goes to the field. We chose a line which is cleaned or renewed in 2018, and another one it was cleaned at 2010. So it shows 2018 the railway line is green. Green means it's clean, and a little bit dark red means the ballast layer is fault, is dirty. So also here we give the indicator, 4 indicators to show it has some trend. So that means our method works in the field, is validated. And then another is about the track geometry. Because the train is running on the track should be in a good position. Otherwise, the train will like a roller coaster or something. So we would like to avoid all these kind of cases in the figure. For example, the track gauge should be always the same. Keep like the accuracy should be in millimeter, and also the longitudinal level, also twisting, cross level, also the rail alignment, left rail alignment, right rail alignment. So these are the key things that need to be measured during this kind of measurement operation. And then we found that the longitudinal level, this indicator, very interestingly, is related with the ballast degradation. So it's the longitudinal level standard deviation. When it change like this, means it's rocketing or something, then that means the ballast layer has some problem. We go to field to dig the ballast to see if the gradation or particle size distribution. And the ballast breaks a lot, aberration a lot. So we found this indicator. That means when we do this kind of measurement, then we analyze the data, then we already link to the problem. Then where is the problem? The ballast has problem, so we go to there to maintain the ballast. So this is the idea. This is the whole process. And also we compared the track geometry data with the ground penetrating radar data, because we cannot dig the ballast everywhere every day. So we here is the track geometry data, the indicator we developed, the standard deviation or the longitudinal level. And here is the ground penetrating radar. When compared these two, and they matched well. For example, here it looks really dark red. That means the ballast layer has problem, at least falling. And then we use the indicator here also with a really high value, and they compare well with each other. And another thing we did about the ground penetrating radar is to how to analyze another way to analyze the ground penetrating radar wave, because sometimes the falling had the water. Sometimes the water contained in the falling has really large influence on the result, because it is electrical magnetic wave. So when water is involved, then the signal is just gone. So we found another way to analyze the ground penetrating radar to optimize it to better show how the falling is, how the ballast layer on the embankment is, their health condition. So first of all, we try to find the best frequency of the ground penetrating radar, and then we proposed developed our new GPR, ground penetrating radar signal processing method, and we found that the scattered waves are much better than the reflected waves. So we try to remove all the reflected waves and only use the scattered waves to analyze the ballast condition. And then we build another track with heavily fouled, moderately fouled, and clean, and to check our theory. And finally, we installed the ground penetrating radar in the wagon, in the train, on the train, and then we go to the field to validate or test our theory. And here is the place we build the track, and here is how it looks like. It takes a lot of time, and then we use the ground penetrating radar to get some data. Then we analyze the scattered waves with this figure. Then we can see left is the track left side, and the center is the track center. Right side is the right side of the track, and then we can see the from the full scale track test. Yeah, it works well. Our theory, then we goes to the field to validate it, and we measured. I think this is 80 kilometers, and in between this is the area with ballast cleaning, and this side it was they were not cleaned, so it shows well. And also we consider the rainfall during the period, and you can see there are some rains, but it still can work well. So finally we developed this to try to remove the influence of the water. And this is about the track, real, because the first figure is when the train is running on the track. Normally, the wire of the rail on the top surface, running surface of the rail is like this. But unfortunately, yeah, this is always happened, and until now there is still no. Yeah, the reason of this is controversial. I mean, everybody think is different reason cause this, but it exists a lot on the in the field. Yeah, you can see it's more like a wave shape wire. We call it corrugation, and this is pretty annoying, especially when you go to the London metro, subway, underground, London underground. You hear really big noises that is caused by this corrugation. And our method is to measure the development of the corrugation and to give a right time when to do the grinding. Grinding is means you make it flat, not like wave shape. To reduce the noises, the whole system vibration, higher vibration means higher damages to all track components. And what we did is we instrumented the wheel side. We installed a lot of sensors and accelerometers on the wheel side to get the acceleration. And then we build the FEM model, finite element method model, and to validate the model, yeah, they match well with each other. And then we developed this indicator to know how serious is the corrugation. Then also we used another more accurate method, yeah, with this small trolley to measure how big the corrugation is. And with this, compared with this, then finally, I think this was 40 results, and there are only 3 errors. And we did just a little bit modification here to make it 0.96 or something. Then it's very high accuracy to give advice or decision of the real grinding. And next, about real management or real inspection, real maintenance is using the 3D imaging. Here the facility, here the laser scanner and wheel reel in the lab, and we get 2D texture image and a 3D depth image. Then we combine these two together, we get 3D image. And what I would like to say is our technology is accurate because we use one camera to get 2 images. Usually they use 2 cameras. One get the 2D texture and another get the 3D depth. But but there is a registration problem because there are two cameras. The two images couldn't register with each other very high accuracy. So with only one camera, in one explorer time, we got two images, and they can register with each other in pixel level. So that means really high accuracy. So we get this 3D image, and then we put them together to get 3D image. Then we develop a machine learning model to analyze, to identify the defects on the rail. Oh, by the way, why we use 3D instead of 2D? Because, for example, in the field, on the rail, sometimes if there is oil or leaves on the rail, if you use 2D and machine learning, they are defined or detected as a defect, but in fact, they are not just oil. But if you use 3D with the depth, then you know it's a damage or it's a leaves or whatever. So this can avoid a lot of misleading decisions or results. And then we developed this machine learning model. Here the frame, and yeah, I guess you guys know this well. With this, first we use this texture image, and depth image goes to this texture branch, and this goes to the depth branch, and then using the machine learning, there are a lot of layers, combine them together, get the feature and all these things, and finally we get this to detect or identify where the defects on the rail. And then we go to the field again. We collect a lot of field data, the damages, the defects, all these kind of things to train the machine learning model, because data is the most important thing. Without data, we cannot do machine learning well. The machine can't learn anything, right? And then we also compared our machine learning model with the existing ones, and the last one is ours, and we are happy to say that we made it very accurate and good. I think we got a really good well-trained machine learning model. It can identify almost all the defects, and also it now it is installed on the train and running everywhere to check the defects on the field. We are still waiting for the results, and maybe, yeah, somewhere this year we could talk about it. And we are still waiting for that, for the validation of the installed on the train. And then the digital twin model. Question is how to build models of various railway components, because, for example, the railway track, the rail and the fastening are steel, sleeper is concrete, ballast, sub-ballast, and subgrade, they are granular material. So with only one numerical method, it's very difficult to simulate it. All these kind of track components. So what we do is we couple the multi-body simulation and discrete element method, finite difference method. They have their strong point, weak point, so we couple them together. So we got all the strong points and avoid the weak points. So here the multi-body simulation vehicle. We borrowed it from Wanming Zhai, his famous theory. And then the discrete element method track, we consider the ballast breakage, degradation in the model, and then how we couple them together. And this FDM finance difference method subgrade, and it is made by FLAC, and the DM track is made by PFC, particle flow code. They are the two software from Itasca. In the software, they have their own interface socket, input and output. They can couple it easily. And what we solve the problem of coupling the multi-body simulation into the DM track, the vehicle and the track coupling. So what we do is when this force is the wheel contact force is running on the rail, so we use these two equations to simulate the forces to all the disks. So when this load or force is moving, then two forces move, become it's a live loading. They are changing. And then with the real equivalent displacement plus the real stiffness, then we can calculate the real forces back to the multi-body simulation vehicle. Then with this method, with this whole loop, we got the two numerical methods fully coupled. And finally, let's watch this video again. Then with what I talked really a lot, and then I guess you can have a better understanding of the video. And that's all. Thank you. Thank you so much.
Thank you. Thank you for that, Yunlong. That was a very interesting talk. Does anyone, I'm going to open it out to the people on the call. Does anyone have any questions that they would like to ask regarding the presentation? Don't be too shy. I sometimes find we just need one question and then they all start flowing in. Anybody, or you can drop it in the chat and I'm happy to read the question out. Obviously, you gave such a good presentation and went into all the details that no one has any further questions on the topic. Anybody? Okay, just while we're... This is a question. Oh, someone's just popped one in. Okay, one from Yu Heng Li. Regarding the GPR, is the method still academic? Has it been applied in the industry?
Yeah, now it's running. Actually, this is already applied in industry for many years, and what we did is try to use it to more useful in different conditions. For example, in the some of the part, for example, in Europe, in the Netherlands, the subgrade is soft and there are a lot of rain. Also in soft part of UK, a lot of rain during the winter, and it has a big influence on the inspection results. And also, sometimes when it goes to the sand fault track, for example, in the Middle East, there are a lot of desert, and also west north part of China, there are a lot of sand and the wind blows sand, but less rain. So that's another case we have solved. So basically, using ground penetrating radar in the railway track inspection has already been existing for a long time, but we did a lot of modifications and a lot of research to make it more useful, accurate, because in the past it's just can when you see the ground penetrating radar, you cannot tell anything actually, and we make the data more meaningful with data signal processing, and also use machine learning to make it more efficient to recognize or find where the defects or problems. Hope this meet your expectation.
Okay, further, so 2 more questions. So further question from Yu Heng Lee. He said, is there any industry standard document we can refer to for ballast cleaning maintenance planning? Do we still need to collect field samples in real practice?
Oh, that's a good question. Actually, my answer is no, because usually the ballast cleaning is based on the annual gross passing the tons. That means how many tons the train passing, and also the ballast cleaning maintenance, it depends on the visual inspection. Just if they see there is already a lot of mud pumping or water, or it's really dirty, then they do some cleaning maintenance. Based on ground penetrating radar, until now, as far as I know, no, there's no standard document. And do we still collect? Yes. It's more like when we validate our ground penetrating radar results, we go to field, dig some holes, collect some samples, sieve it, and to compare it with the ground penetrating radar data results. And also, this is mainly for the decision making process, because they have to go to field to dig some hole to see what is going on inside, to decide if the ballast cleaning is needed. And also, I know in UK there is a Panda or something, is like drill a hole to easily collect sample, like the I can type it, Panda, but it's also destructive to the track. Even though you just dig a small hole, penetrate a small hole to collect some sample, but it is still destructive to the track. So I hope someday. Oh, really? Can I just penetrate it and then do some sieving or something?
Do the people that want to put the comments on
Okay. Anyway,
come off mic?
maybe I made a mistake. Sorry. And Panda. Okay. Thanks for your explanation. Maybe I made a mistake, another name or something. And as far as I know, is sometimes it's too destructive to the track. So it's better to. I hope someday will be a standard or something. At least it can as an add-on to the railway track maintenance, because normally now it's periodic, like 1 year or 2 years do some tamping, and maybe 5 years they go to the cleaning if it is too serious. For example, transition zone or somewhere is too dirty, or switch and crossing part there is impact loading, or joint part is always the joint has a problem, and then they do some cleaning or whatever. So I hope this could be an add-on to all these standards, at least fusing all this data, and then give a more accurate decision on this track maintenance.
Okay, Colin, you had your hand up. I noticed you dropped it down. Did you still have a question, or?
Interested on sort of more guidance documentation, I guess. We in the rail industry, obviously, we do use GPR to look at ballast cleaning and deeper subgrade, although I think it's quite specialist knowledge, and I wouldn't proclaim that it's sort of well understood across the business, although there are obviously specialists. I think there's a couple on the call. One of the things I'm interested in is, you talked about the AI learning. we're obviously all tied into our individual company sort of policies around how we use sort of machine learning. I'm just interested to know, presumably all the different companies and universities are using their own approach. I think Zetica have an approach, and I'm guessing that everybody's kind of doing things in isolation. I mean, obviously in university you'll have access to different tools. Is there specific code that's being used or developed, or you're all sort of developing things around your personal need? And you talked about roughness. I think I wouldn't proclaim to follow it all, but roughness coefficients and items around sort of flak analysis with the wheel and axial loads that you talked about. I'm just interested to understand, where's the coding and machine learning? Is it sort of siloed? Are you doing it individually in university or with certain companies?
To be honest, we develop some of the code ourselves, because we did use some online code. You can find it at GitHub or somewhere. There are a lot. You can even have a code with ChatGPT. It's easy, and but when we got the code, they are not quite useful, because we have to do a lot of modifications. And we have to rewrite the code and to be adapted to our cases. For example, if you can always use YOLO to recognize all kinds of things. It's very popular. YOLO V now is maybe V10 or something, I don't know. And but for our certain cases, we have to, for example, like we recently we did the combine the using machine learning for the ground penetrating radar data, the images, and because for example, like we have a lot of images, ground penetrating radar images, defect images of this kind of mud pumping or water, a lot of water in the ballast layer, but there are some defects are not enough training data. So we have to use like transfer learning or other kind of method to train the model well. And we sometimes it's not easy to find the right one, and it's kind of by luck to find the right network or whatever. This all you combine all this network, how you combine it finally to get the right one. It's kind of need a lot of experience. Sometimes it's kind of feeling how you build this machine learning model framework. So my question is, yes, we did a lot of work on developing this machine learning model. And
I guess you have to kind of invest the time, don't you, if you want it to become make it more efficient. You have to invest the initial time in teaching it what you need to see and what you need to spot and what you need to discount. So it's interesting, and I wonder if internally we probably need to invest some time and effort into doing exactly that, so we can make better use of the GPR information. Just one more thing, sorry. I know that we look at directly down from the train. Do you do work looking at, I guess we try to pick up some of the crest to understand more about the track formation relative to maybe the embankment crest or earthwork. Do you do much work where it's mounted in such a way that it picks up more of the crest of the bank relative to the track, sort of the cess area?
We installed two frequency. One is 2 gigahertz. Another is 400 megahertz.
Yes, yeah.
And so the 400 megahertz can go deeper to the embankment, and the 2 gigahertz is more like to the ballast layer, because it can only detect. I remember it's half a meter or something.
Yeah,
half a meter. And
always directly down, is it? Always directly down through the 4 foot, or is there opportunities to mount it in such a way that it picks up, so the crest of the bank.
Yeah, yeah, of course. And the embankment, to be honest, is sometimes when we build the railway track, the embankment or the subgrade is already given. So here the subgrade build your track or something. So we sometimes when we solve the problem, for example, like we can use ground penetrating radar to know the ballast layer thickness. So this is very important because sometimes when we do the maintenance, for example, in Netherlands, we do the maintenance after tamping, we just add more ballast. Especially for the transition zone, we just when there is more sediment, ballast goes down, we just add more smart ballast. But in Netherlands, the subgrade is really soft. Then if you add more ballast, then that means heavier than before, and then it settles even more quickly.
Propagates the problem.
Yeah, so use ground penetrating radar to know the thickness, and all these kind of cases are very important. And by the way, for the 400 megahertz ground penetrating radar, it can go deeper, but the let's say the details of the data are not that good because it can go deeper. Its wavelength is longer than it can just I mean I don't know how to describe it. Just to avoid something, that means the details are gone because the wavelength is long. If a shorter wavelength it goes everywhere, then it can detect more things. So there are some advantages of the high frequency and the low frequency ground penetrating radar, but that's too details about the technology.
Thank you.
Okay, any more questions? I think Yuhang Lee's asked if he could have your email address because his organisation has some specific questions regarding the previous topic. So if you're okay to drop it on there, that'd be great. Anybody else got any questions before we close the meeting? Okay, just to let everyone know, so next month we have a talk on the ETCS data integration, and that's going to be done by Mark Weldley. So he's a senior engineer in the digital transformation team for Network Rail, and he's also a subject matter expert for the ETCS for the Network Rail training. So that talk will take place on the 10th of April, same time, lunchtime, 12:15 to 1:30. So it'd be great to see as many of you there as can be. On that note, as there's no more questions, then I will leave the meeting there. So thank you very much, Yunlong, for your in-depth presentation. I found that very interesting. I'm sure everyone else did. Thank you for your time. So the PWI thanks you, and hopefully we will see you again soon.
Thank you. Thank you so much. Thank you.